All right. By the way, we saw very briefly parent function on Friday. Parent function just means the simplest form of a particular type of graph. So if we're talking about absolute value, that would be f of x is equal to the absolute value of x. You can see right up here. If we're talking about linear, the simplest form would be f of x. That would be the blue line right here. That would be a slope of 1 and a y-intercept of 1. If we're talking about quadratic, it would be f of x is equal to x squared. There's no other numbers aside from the x and then whatever symbols we need for that particular one. So it says changing the parameters for the values of a, h, and k in a function. I'll talk about what those mean during the lesson, but we're just going to see what those look like today. Changing the parameters in a function, and the function that we're going to be changing the parameters for is the g of x function. F of x will be the parent function for each of these, absolute value, linear, and quadratic. G of x will be the one that we're actually going to be messing around with the values of h, k, and a. Those are going to be on those sliders right there. And there's a form of a function that I will teach you about over the next couple of days, but it's right here. And it's in the form g of x is equal to a times f of, f is not a variable, f of would be the function itself, f of x minus h and then plus k, changes the graph from the graph of the parent function. You can use the sketch to explore the effects that changing the parameters has on the shape, the vertex, and the axis of symmetry of linear, quadratic, and absolute value functions. So everything that we do here is going to be a little bit different. So if you notice this first one here, this g of x, and then it says f of x minus h, but you'll notice with the absolute value, it says g of x is equal to a times, and then the absolute value of x minus h. Now, the x minus h here, it could just as easily have that little f on the outside, but it doesn't have it. It can include it or not. F is not a variable. It's just saying we're talking about how it's acting upon the original function. So how does g change the original function? That's what we're talking about. So you won't see that here, but sometimes you'll see it written out as well. Generally, it's going to mean the same thing. So let's go ahead and just scroll down. We'll look at exercise 1. It says press absolute value. So if you haven't done that already, hit the absolute value button. Do that to explore how the parameters affect the function. Drag point k along the slider to see what happens when a value is added to the function. Examine the change of the graph for g of x for various values for k as compared to the parent function, f of x is equal to the absolute value of x. So just go ahead and move things around and see what happens. So let's just talk about k for a second. What happens if you move k? What is the graph doing when you move k? Going up or down, right? Yeah. So the value of k, at least in this instance, seems to affect the height of the graph, or at least where the vertex is, right? So we're talking right down here. It says describe similarities. What are the similarities between the parent function in blue and the translated function in purple? How are they similar? How are the blue and the purple functions alike? I mean, they're not entirely different. How do they look similar? They're both V-shaped, right? F of x is facing up, G of x is facing up, but they're both like straight up V-shaped graphs. They each have a vertex, but you know, there's a lot of differences here. But in terms of similarity, they have the same general V shape to them. So similarities and differences. Well, the similarities is that they're both V-shaped graphs. The differences are much more than the similarities, though. The V-shape has been turned upside down for g of x. The value of k can definitely change where it's at. Now, in terms of the actual number, how does the actual number affect how far up or down it goes? Anybody kind of figure that out? Like if k is equal to, if we can get there's a decent one here, 2.25. What do you notice about the value of k versus where the graph is on the grid? K value of 2.25, what do you notice? How does that number relate to the somewhere on this purple graph? Okay to use words. Or if we move it negative. How does this end up relating? There's a negative 1.98. What do you notice about the purple graph at this point? If it's a negative 1.98, which is basically negative 2. Start calling on random people. What does it appear? What does that relationship seem to be? It certainly seems to be the y-intercept at this point. Now, it may or may not end up being the y-intercept, but it certainly seems to affect, at least, at this point, if it's a negative number, it seems to be moving it down the graph. If it's a positive number, it seems to be moving it up the graph. And in this case, it does seem to be the y-intercept right now. Now, that might change depending on other values, a and h, but for now, it does seem to be that way. What about values of, what does it say? Move the values of h, I think it says. Yeah, drag point h. What's h doing? What's that? So I'm looking here and I see 2 x-intercepts in terms of where I have my graph currently. And there doesn't necessarily seem to be a strong connection, because if I move the graph up and down, the x-intercepts are changing. And so if I use k, if I change k, the location of the x-intercepts are definitely changing. So that doesn't quite seem to be exactly what's happening here, but what does it look like h is doing as we drag it left and right? What's happening with the graph if we move h around? Kesley, what's the graph doing as we move h? Yeah, it's moving it left or right, right? K is changing it on the y-axis. H is moving it on the x-axis. Now, Bryce mentioned that it appeared that we had a y-intercept when we were changing k, but what happens if I move this over to, let's say, 5 on the x-axis? And if I move this up to, let's say, 2.05, is my y-intercept at 2 right now? No, it's negative. Okay. What is at a height of 2 or about 2 on my purple graph? What point is this right here? What do we call that point? That's the vertex. And then h is a value of 5. How far over is the graph on the x-axis? 5 over. How far up? 2. So what do you think h and k have to do with? The vertex, yeah. H and k give you the location of the vertex. That is true about this type of a function. Now, something I want to point out is, look inside the parentheses, or I guess in this case, the absolute value. It doesn't say x plus h, does it? It says x minus h. So if you were to write this function, you would have x minus 5 in the absolute value, because it's a minus there. And we would have plus 2.05 on the end. So when we get into the notes today, you're going to notice that changing a k value, if it's a plus, that means it's been moved up. If it's a minus, that means it's been moved down. However, if it's inside your grouping here, the minus, because you're subtracting the positive value of h, it's kind of like backwards from what you might think it would be. If it's a minus, that means h is positive, which means it's moving left. If it's a plus, that means that h is minus, plus means going to the right. Minus means going to the right because it's a positive value. Plus means you're going to the left because h should be a negative value. It's a little bit backwards from what you might expect. And then let's talk about a real quick. What do you think the value of a does? I think that's probably what's next on here, right? Yeah. What does a do? Anybody mess around with a yet? What does it appear that a is doing? Yeah, good. It definitely changes the slope, or I guess steepness might be a good way of saying it. Because if we're getting technical, absolute value and quadratics don't have slope, but they do have steepness. So as we go away from zero, is it getting wider or narrower as you go away from zero? Narrower. Okay, and as we get close to zero, closer to zero, closer to zero, closer to zero, it's getting really wide until it goes positive, and then as it goes away from zero again, it gets narrower. So regardless, if you have a big positive value or a big negative value, it's going to be pretty narrow. If you have a very small positive value or a very small negative value, it's going to be a very wide graph. So definitely the width of the graph, the steepness of the graph is determined by the value of a. What else appears to be determining part of the graph because of a? How else is the graph changing based on the value of a? Yeah, whether it's facing up or down. If the graph is facing upward, a is positive. If it's facing like upside down, then a is negative. All right. Now this is some stuff that you saw back in Algebra 1, but not to the level of detail that we're going to do this morning. If we go to exercise 4, going to move us on. So which values of a make the function wider? We just said as they go away from 0, they get narrower. So which values of a make it wider? Farther away from a is narrower, or sorry, not farther away from a. Farther away from negative is narrower. So wider would be closer to 0. Yeah, values that are closer to 0 make it wider. Values that are further away from 0 make it narrower. All right. Let's see. Which values of a make the function open up? What kinds of numbers would make the function open upwards? Positive. Downwards? Negative. All right. What else do we have here? Press linear. And then we're also going to do this for quadratic as well. So let's go ahead and just mess around with linear now. So linear, back to our normal. The value of k, we were able to see earlier that it generally will move the graph up or down. So let's see if that's true. Yeah, k seems to be moving the graph up or down. H, we said, looks like it moves the graph left or right. Look at that. H is moving the graph left or right. And then this time, Julie, we can use the word slope because we're talking about lines. And so if we talk about a, if we make a really negative, it gets to be a very steep slope. But it's a negative slope. And as we get closer to 0, the slope gets shallower and shallower and shallower. It's still a negative slope until it goes positive. And then it's a shallow slope positive, and it gets steeper and steeper and steeper as we get away from 0. For quadratic, let's see if this stuff stays the same. Value of k, moves it up, moves it down. Value of h, moves it left, moves it right. And the values of h and k determine the location of the vertex. H is over here with a 4.96, and k is down at negative 2.18. That's the vertex of the parabola. If we mess around with a, as we go further away from 0, negatively, it gets very narrow upside down. As we get closer to 0, it gets wider and wider and wider until it goes upwards, because now it's positive. And as we go away from 0, it gets narrower and narrower and narrower. So those values, those are the main values and the main transformations that you will see with graphs. And like I said, I'm going to leave all of this up here as we start in on the notes over here. So go ahead and close up your Chromebooks. I'm going to leave that graph open, just so we can keep referring back to the visual. And we're going to open up page 57. And we'll spend the last 20 minutes or so working through a couple examples here. We'll definitely finish up these notes tomorrow. And your 1/6 lesson is also due tomorrow. If you're done with it, feel free to turn it in. If you're not done, keep working on it. Get it in by tomorrow. All right. So this entire final lesson, of this unit is based on 3 types of functions. We're going to be looking at 3 types of functions: linear, absolute value, and quadratic. That's it. We're not going to be seeing the cubic functions or anything like with a bunch of, dips and maxima and minimum or anything like that. We're just going to be looking at 3 basic types of functions: linear, absolute value, and quadratic. And so we're going to start off with a definition of family of graphs. A family of graphs and equations of graphs that have at least one characteristic in common would be part of the same family of graphs. The parent graph is transformed to create other members in a family of graphs. So a constant function is a type of linear function, but it's just a horizontal line. So f of x equals a number, there's no x. Or y equals a number, there's no x. The general equation would be f of x is equal to a, and depending on what a is, it changes whether the graph is positive or negative, but it is a horizontal line no matter what. So your domain is going to be all real numbers, and your range is going to be exactly what the y value is, because that's the only y value for a horizontal line. That's what we're talking about there. The identity function is f of x is equal to x. It's the most basic straight line you can have. Slope of 1, y-intercept of 0, just a perfectly diagonal line with positive slope, slope of 1. F of x includes all points with coordinates AA. Basically what that means is whatever x is, y is. X and y will always match if you have the function f of x equals x. Because if you go up 1, you go over 1. You have the point 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, -10, -10, and so forth. It is the parent function of most linear functions, most. The domain is all real numbers, the range is all real numbers. It goes left and right forever, it goes up and down forever, so all real numbers for both of those. Absolute value, we saw this a little bit last week. We've got ourselves the parent function, which is just the absolute value of x. The most basic form of absolute value is the absolute value of x. Nothing else, no other numbers are being acted upon it. We've got a domain of all real numbers, because it goes left and right forever. However, the range, this is just for the parent function, by the way, the range is f of x is greater than or equal to 0. It goes down to 0, goes back up. All the y values are 0 or more than 0. And then the function of a quadratic has very similar key features, but it looks pretty different. X squared is a parabola as opposed to a v-shaped, and f of x equals x squared, the most basic form of a quadratic function. However, the domain and range are exactly the same because, well, they go left and right forever, and it goes down to 0 and then turns back up. Except this one is not v-shaped. This one is a u-shaped graph because of the exponent, as opposed to this one not having an exponent. So, as we saw in the warm-up, here are some things to know. The value of k, as we saw, translates, moves the graph. Translate means moves. If you add a value in the, quote, like k position, meaning if you add a number basically to the end of the function, and the number at the end of the function does not have a variable or anything like that, that moves the graph up. It translates it a certain amount of units in an upward direction. If you add a value of k that is less than 0, then the graph gets translated down a certain amount of units, an absolute value of that certain amount of units. Now, the other way to write this would be, go ahead and put this down as well, f of x minus k. Because it will not show up in the function as a plus, a negative, it'll just show up as subtraction. And so if it's like minus 2, that means it's been moved down 2 units. If it's a plus 4, it means it's been moved up 4 units. How is the positioning of h in the function different than the positioning of k? Because this is kind of a big idea with moving graphs around. How is the positioning of h different than the positioning of k in terms of where it appears in the function? It's in the parentheses. Yeah, it's part of the group. The k was not within the group. So, by the way, f of x is the same thing as what? F of x is the same thing as y. So whatever the y value is, add a certain amount to it, it makes it go up. Whatever the y value is, subtract a certain amount from it, it moves it down. This is saying we're not changing the height of the y value because it's within where the x is. If it's within where the x is, we're not moving it up or down because we're not taking the y value, the whole y value, and adding or subtracting to it to make it go up or down. We're taking what makes the y value, and it's going to end up moving it left or right. That's why it's within that group. And we talk about this briefly over here, but if your h value is positive, we know it moves it to the right because positive on the x-axis is to the right. However, within the actual function, the standard form of that function includes subtraction, not addition. Meaning, if you have, back to the paper here, if you have a positive h value, it will show up as subtraction within the parentheses. That means you're moving it to the right. This is a positive value of h because subtraction is part of the equation, not addition. Likewise, if you have, it's probably going to appear, or not even probably, it will appear like this, f of x plus h, which is not part of the normal function. Addition is the opposite of what's normally there, which means that your h value is negative, which means it's moving left. If you have a plus within the group, that means you're going left. If you have a minus within the group, that means you're going right. If you have a plus after the group, it means you're going up. If you have a minus after the group, it means you're going down. So directionally, things feel backwards when we're talking about horizontal translations. Horizontal meaning left or right. If you change where the x is on the x-axis, it's going to feel a little bit backwards. For the y values, it just kind of makes sense with what you think. Plus means up, minus means down. But with x values, minus means positive, and plus means go negative. All right. Let's keep going. Now we get to talk about, and this is why I left the graph up here. So it says, describe the translation in g of x, the red one, as it relates to the graph of the parent function, f of x, which is the blue one. So if I go back over here to quadratic, and we are not changing the a value. First of all, there is no change in an a value here because an a value is always multiply at the front side of the function, which there is no multiplication outside of the grouping. But we do have a subtraction of 4, and we do have a plus 2. The subtraction of 4 is afterwards, so that's going to be a k value. And so you move that down 4, as close to 4 as we can, I should say. Our a value, what's our a value here if there's no value of a multiplied on the outside? If you don't have a number, what number would you multiply to not change something? 1. Okay, so a is 1. Not really important to this problem, but it is important for this graph here. So I'm going to make this an a value of about 1. And then we have an h value. It says plus 2, which means h would be negative 2. I'm going to get as close to negative 2 as I can. So if you look at the graph over here and you look at the graph there, those two things are roughly the same. Obviously, I can't get the exact values for h, k, and a because I can't type them in, but that's what we're looking at. Those two things mirror one another. So since g of x is quadratic, the parent function is f of x is equal to, what's the parent function of a quadratic? Right here. X squared. All right. Parent function of a quadratic is always f of x equals x squared. If it's quadratic, it's x squared. If it's absolute value, it's absolute value of x. If it's linear, it's just x. Since f of x is equal to x squared, g of x is equal to f of x minus h plus k, where h is equal to, what's our h value? Look over on the slider. But give me the whole number. -2, okay? H is -2, and what's k? What's our k value over here? -4. The constant value of k is added to the function after it has been evaluated. You're adding it to the y value so that k affects the output or the y values. If you are subtracting it, that means that k is less than 0, so the graph is translated what direction? If k is negative, k affects up versus down. K is a negative value, so it moved it down 4 units. The value of h is always subtracted from k before it's evaluated. And since it's less than 0, that means we're moving the value of h 2 units. Well, what direction did the red graph move from the blue in terms of left or right? Did it go left or did it go right? It went left. 2 units left. So the graph of g of x is equal to x plus 2 squared minus 4 is the translation of the parent function, 2 units left and 4 units down. So that's how you would describe what has happened to the parent function. You'll see questions like this. Describe the translation of the parent function. And so if you have the parent function and you have your new function, the only thing that's changed is the vertex. The vertex went from 0, 0 to -2, -4. And these are the values of h and k. H and k give you the location of the vertex. It tells you a translation, a movement of the graph. Left 2, down 4. That's the only difference between the parent function and g of x here is it's been moved to the left, down 4. So the vertex is now at -2, 4 versus 0, 0. Any questions about that before we look at the absolute value for example 2? Let's take a look though. Identify translated functions from graphs. So now we've got ourselves the parent function in blue and the transformed function or translated function. By the way, a transformation is any change to a function. A translation is a movement, just moving it around. There's no reflections, there's no changing of the width or flipping it upside down. A translation is just a movement. So the graph of the function, use the graph of the function to write the equation. All right. So the graph is an absolute value function with a parent function of f of x is equal to the absolute value of x. That's always the simplest form you can possibly have. And since it's absolute value, we take the absolute value of x. That's the blue one. Notice that the vertex of the function has been shifted both vertically and horizontally from the parent function. Figure out a translation, figure out where the vertex was to where it is now, and that will give you your translation. Kind of like what we just talked about here. -2 for h, -4 for k. To write the equation of the graph, determine the values of h and k in g of x is equal to the absolute value of x minus h plus k. The translated graph has been shifted 2 units up and 1 unit right. So we have our original vertex at 0, 0. And then the new vertex is where? What is that coordinate there of the new vertex? 1, 2. So that means we have an h value of 1 and a k value of 2. So h equals 1, k equals 2. So something you can do as well is you can always start off by writing x minus, and then just leave a blank. That's not a 1, by the way. That's the absolute value. Always start with x minus inside your group. If it's been moved in a positive direction, you just write the number after the minus, because the minus is part of the formula. So it'll be x minus 1 in the absolute value. If it was a negative 1, you'd change the minus to a plus and then just put a 1 after it, because, again, when it's in the grouping, it feels a little bit backwards. And then it's been moved up 2 on the y-axis, so we're going to write plus 2 or minus 2 after the absolute value. Plus. Up and down feel normal when we're talking about values of k. So we got the absolute value of x minus 1 plus 2. If we do that over here, we're going to get make a equal to 1-ish, and so we've got a k value of 2, as close to 2 as I can, and then an h value of 1. About right there. So those two graphs do the same thing. Any questions so far about h and k in terms of what they do? H and k shift the graph or translate the graph or move the graph. Move, shift, translate, basically all mean the same thing. All right, moving on. A dilation. We'll just talk about this briefly, and then it's actually not a super long lesson. I just wanted to get a lot of setup work done today. So dilations and reflections. And the reason why we're talking about dilations and reflections at the same time is because dilations and reflections are oftentimes controlled by the value of a. If there's a number being multiplied at the beginning of the function, a value of a, that will change, as we saw over here. That's going to change how steep the graph is or how wide the graph is, narrow or wide or steep or shallow, however you want to call that. So the width is controlled by a, as is whether it is facing up or facing down, whether it's positive or negative. So now we're going to talk about a. So a dilation is a transformation that stretches or compresses the graph. So a stretch means narrow. If you're talking about a stretch or a compression, stretching it makes it narrower, compressing it makes it wider. Narrower versus wider. Multiplying the function by a constant value. So if you multiply the whole thing by a certain value, the constant dilates the graph with respect to the y-axis. Multiplying the independent variable. Which one's the independent variable? X or y? Which one? X. Yeah, the independent variable is x. If you multiply that by a constant, then that will dilate the graph with respect to the x-axis. It just depends on where the multiplication is happening. If you are multiplying the y value, that's one of these first two things. Because if you multiply a times f of x, that would be whatever y is, f of x multiplied by a certain number. Now, if the absolute value of that number is greater than 1, it's going to stretch the graph vertically, meaning narrower. It'll make the graph narrower. As the value of a gets larger, either in a negative or a positive manner, it's going to make the graph narrow. As we get further away from 0, let me go back over here. As we get further away from 0 in a negative direction, it makes it narrower. As we get further away from 0 in a positive direction, it still makes the graph narrower. That's what we're saying. Now this is right here. If the value of a, or the absolute value of a on the other hand, if the absolute value of a is between 0 and 1, that will make the graph wider. So once you get to 1, it gets compressed. It gets compressed more and more and more and more. So, and even here, negative 0.2, that's a pretty wide graph. So narrower, and we're going to say wider. And the reason why it's in reference to 1, by the way, greater than 1 versus less than 1, the reason why we're referencing 1 is because 1 means that there is no value of a. Right? The values of 1, this one had an a value of 1 because there's nothing out there. Multiplying by 1 doesn't change anything. So it doesn't make it narrower or wider because it's just 1, and 1 doesn't make a difference with multiplication. On the other hand, if you are multiplying your independent variable, your x value, notice that the a is not multiplying the entire y value, it's only multiplying the x value on the inside of the group. That is going to compress the graph horizontally, which will look on the graph as narrower. Because basically, this isn't gonna it's an easy way to think about it, but it's not like a very mathematic way to say it. But a vertical stretch oftentimes looks like a horizontal compression. So those two things, most of the time, will make the graph look narrow because they're basically doing the opposite things. If you stretch a graph vertically on the y-axis, it makes it narrower. If you compress a graph horizontally on the x-axis, compressing it on the x-axis is not doing this, it's doing this. Compressing on the x-axis does that, which, again, makes it look narrow. A compression on one axis is the same thing as a stretch on the other. And so this last one will make a graph generally look wider. We're going to pause here, and we'll pick up things tomorrow. And we'll finish this lesson. I'll have you turn in 1-6 tomorrow as well.